All right, next we will discuss how to do calculus with parametric equations, and in particular we will discuss how to do differentiation. So the setup will be very standard for this section. We're going to have a parametric curve defined by the following set of parametric equations. So we will have a parameter t and two functions that represent x and y, and recall that the following is what we call the derivative of x, and we write it as dx dt. So the following quantity represents the rate of change of x coordinate with respect to time. So this quantity basically tells us how fast x changes. And similarly, this quantity, the derivative of y with respect to t, is the rate of change of the y coordinate with respect to t, the parameter t, which I call time, but it doesn't have to be time, but just the parameter t. And the goal for us is to come up with an expression for dy dx, which, if the function given explicitly, can be obtained by simply differentiating the function. But since the function is not given to us explicitly, how do we express this quantity given what is given? And the answer comes from actually applying the chain rule to let's see. So according to the chain rule, if we want to differentiate the let's say if we want to take dy dx, or rather, hold on. So if we assume for a second that y of x did exist as a function, so that means we have y of x, and x being a function of t means we can hypothetically write it like this. And now if we were to differentiate this, then we would apply the chain rule that will tell us that this will be the derivative of y with respect to x multiplied by the derivative of x with respect to t. So using the Leibniz notation, this can be written as dy dx and multiplied by dx dt. And of course here I should say that we integrate differentiating with respect to t. But this is, per chain rule, is the derivative with respect to x, and this is the derivative with respect to t. So here's what we get. We are looking for dy dt, and according to the chain rule, it is equal to this. Now, all we have to do is isolate this expression, and we end up with the desired formula. So dy dx can be expressed as dy dt over dx dt, where y and x are as given in the parametric equations. So this quantity, as it looks, represents the rate of change of y with respect to x. So let's do an example. So in the task here is to find the slope of the tangent line at t equals 1. So first of all, what does it mean to find the slope of the tangent line at t equals 1? It has two parts, so we will find the slope, but let's for right now focus at what does it mean at t equals 1. So at t equals 1 means we're looking at the following point that can be expressed this way, and x and y both can be evaluated at 1, and the x will be 1 plus square root of 1, and the y will be e to the power 1 squared. So when we are asked to find the slope of the tangent line, we are asked to find it at this point, 2, e. But anyway, the process of finding the slope of the tangent line starts with finding the expression that corresponds to this. So the slope is the derivative. First, let's find the derivative, then we will evaluate it at that point. And according to the formula for the derivative of y with respect to x, we have to first compute the dy dt. So what is dy dt? Let's do it separately. So let's compute dy dt. It's going to be the derivative of e to the power t squared with respect to t, and it will be 2t e to the power t squared. And similarly, let's find dx dt, which is the derivative of 1 plus square root of t, and it's just going to be 1 over 2 square root of t. So putting it all in to this formula, we get 2t e to the t squared divided by dx dt, which is 1 over 2 square root of t. So combining it or rewriting this fraction in the simplest form, we get 4t to the power 3/2 times e to the power t squared. So this is the expression for the derivative. We still need to evaluate it at 1. So when t equals to 1, this expression becomes, or this expression is the slope of the tangent line at that point. So this expression becomes 4 times 1 to the power 3/2 e to the power 1 squared. So it's just 4e squared. Not squared, but rather just e, because 1 squared is 1, not 2. So this is the answer to this question using the formula for the derivative that we developed here. If we want to check this work, check our work using calculus of explicit functions, here's what we can do. We can rewrite y as a function of x. So we're going to isolate t from the first equation. So t is equal to x minus 1 squared. And then we can plug in this t into the equation for y, and therefore write it as a function of x. So it will be e to the power t squared, but t is x minus 1 squared, so it's going to be x minus 1 to the power 4. And now if the question is to find the slope will be equal to the y prime evaluated at x. Which x? Well, earlier we determined that all of this is happening when x equals 2, and to find the slope this way, when the function is given to us explicitly, we have to differentiate the function first. So 4x minus 1 cubed times e to the power x minus 1 to the 4th. This is us differentiating it, and now this is us evaluating this function at 2. So we get 4 times 2 minus 1 cubed times e to the power 2 minus 1 to the power 4. And we also get 4e, which is our desired slope. So we found it using two different ways. One, using the formula that allows us to find the dy dx for a curve given parametrically, and we also did it directly. So not always you will be able to isolate the variable t and plug it in for function into the y function. So not always you can rewrite the parametric equations in explicit form. So sometimes we will have to use the method for parametric equations. All right, let's do another example. So we have this curve. And this time we're going to find, we're not going to find just the slope, we're going to find the equation of the tangent line at when t is equal to pi over 2. So again, first of all, what does it mean to find the equation of the tangent line at t is equal to pi over 2? So we're talking about this specific point on the curve, and let's find it. So evaluating x at pi over 2 gives us -1. Cosine of pi over 2 is 0. Cosine of negative or of pi is -1. Same thing here. Sine of pi over 2 is 1, and sine of pi is 0. So this is the point where everything is happening. And to find the equation of the tangent line, we're going to use the point slope formula. So this is the formula that we're going to use. And we already found the x and y of the point. So the only thing left is finding the slope. To find the slope, we're going to use this formula. It's going to be the dy dx evaluated at this point. And first we have to find the, let's go this way. So we're gonna break it up into steps. So now, in order for us to evaluate the derivative at that point, we have to find the derivative. And to find the derivative, we're gonna have to use this formula. And in order for us to use this formula, we're going to differentiate the y function and x function with respect to t separately. So dy dt is cosine t minus 2 cosine 2t. I'm using the chain rule. And dx dt is negative sine t. This should be positive here. Minus 2 sine 2t. I'm also using the chain rule. So we're now plugging it all in. So dy dt cosine t plus 2 cosine 2t goes here. Negative sine t minus 2 sine 2t goes here. And now we're going to evaluate it all at the point -1, 1. But that's the same as evaluating all of this at t, and the t is equal to pi over 2. So, continuing by plugging in pi over 2, 2 times that will be equal to pi. And now let's evaluate this. Cosine of pi over 2 is 0. cosine of pi is -1, so we have -2 on top. Negative sine of pi over 2, that's -1, and sine of pi is 0, so we get -1. So the slope is actually 2, and now we're finishing it off by plugging everything into this point slope formula. So y minus 1 is equal to 2 times x minus -1. So the final answer is we distribute this over, so 2x plus 2, and we bring 1 over to the right, so the final answer is this. So this is the equation of the tangent line to the graph of this parametric curve when t equals pi over 2. Let's do another example, and this time we will be given a simple parametric a set of simple parametric equations, but the question is to determine all the points on the curve where the tangent lines are horizontal or vertical. So find all the points where the tangent lines are horizontal or vertical. So we're going to find them all. And what does it mean for a tangent line to be horizontal? So we can rephrase this question, and horizontal actually means the slope of the tangent line is equal to 0. And what does it mean to be vertical? Vertical lines don't have a slope. So what are we going to be looking for? We're going to be looking for tangent lines which are not defined, and one way in particular to be not defined is when you have division by 0. So we're going to be looking for those slopes that are undefined. I guess I will put it as undefined here. And in particular will be interesting in something like when we have division by 0 going on. So in order for us to find the slopes that satisfy these conditions, we first have to find the general expressions for those slopes, and we're going to be using the formula. And since we already know we're going to be using this formula, I guess we can just start setting it up. So the slopes will be equal to dy dx, and then dy dx can be rewritten like this, and then differentiating dy with y with respect to t will get 3t squared minus 3, and differentiating x with respect to t gives us 3t squared. I have a typo here, sorry, this should be squared over here. So dy dt will be minus 6t, and dx dt is 3t squared minus 3. And now we're going to simplify this a little further. So we're going to factor out 3t, t minus 2, and we're going to factor out 3, and it's going to be t minus 1, t plus 1. And the question is when all of this is equal to 0. And it will be equal to 0 when the numerator is equal to 0. So it will be equal to 0 when t is equal to 0, or t minus 2 is equal to 0, which means t must be equal to. Alternatively, we may ask ourselves, when is this undefined? And one way to make this undefined is to make the denominator equal to 0. So when t is equal to 1 and t is equal to, or t is equal to -1, this is when this expression is undefined. So what appears from this analysis is that we're going to have a horizontal asymptote in this case. Sorry, not a horizontal asymptote, but horizontal tangent line. And we're going to have a vertical tangent line here. But since the question was asking us about find the points, so to find the point, we're going to actually plug in those t values into the parametric equation. So when t is equal to 0, we get 0, 0. When t equals 2, we get 8 minus 6 is 2, and 8 minus 12 is -4. And now we do the same thing with 1 and -1. So when we plug in 1, we get (1 minus 3 is -2). And when we plug in 1 into y function, we get also -2. And now we plug in -1, so we get -1 plus 3, it's 2. And we get -1 minus 3, that's -4. So we found the points where the tangent line is horizontal and vertical. And sorry about that, having an issue here with zooming. If you're paying attention here, the question now that you should have is, what is going on at 2, -4? How on earth it is possible to have a tangent line at 2, -4 that is horizontal and vertical at the same time? And to answer this question, we're going to have to look at the graph of this parametric curve. To graph it, I'm going to use Desmos, and we're going to go and enter all these equations, and let's find out what's going on at this point. So we're looking at the point -2, -4. So where is that point? So let's extend this domain of t a little further, and what do we notice here? We notice that at 2, -4 we have the following behavior. We actually have the following graph. So again, this is the parametric curve, and turns out that it passes through the point 2, -4 2 times. So of course it's possible to have two tangent lines. One is vertical, one is horizontal, when you pass through the point 2 different times. And what does that mean? That means that this parametric curve is not a function, but it is still a curve, and we can still do calculus with it. All right, so let's start the conversation about some other tasks that we can perform using differentiation, and I'm talking about determining the concavity of the graph with the second derivative. Or in other words, how do we define the second derivative for parametric curves with given parametric equations. We're going to have the same setup. So we're going to have a parametric curve, and for this parametric curve, we already know that the dy dx is defined by dy dt over dx dt. What are we interested at? We're interested in actually finding the second derivative of y with respect to x. But how do we find the second derivative of y with respect to x? Well, we take the first derivative of y with respect to x and we differentiate it with respect to x. So if we for a second call the derivative of y with respect to x something else, like let's say z, so what we're actually looking for is dz dx. And if z is a function of t, which it is, then we can use the formula that we just established, this formula, to find the derivative of dz dx. So it will be dz dt over dx dt. But what is z? Z is actually dy dx, and dz, well, z, so dy dx, as we just found it earlier, is dy dt over dx dt. So putting it all together gives us the following formula, which is pretty intimidating. There's a lot of going on here. So we have dz, and we're taking, so this is our dy dx. It's a function of t. Then we take this and differentiate it with respect to t again, and then we divide all that by the dx dt. So as a formula, it's pretty heavy, and you don't need to memorize it. What you need to understand here is the process of finding the second derivative more than anything. So let's practice the process, not the formula, and let's find the second derivative for the following set of parametric equations. And let's not just find it, let's also use it to determine the concavity. And let's get started. So the second derivative of y with respect to x, it's the same as the derivative of the first derivative with respect to x. And if we again, let me do it slow here, so we can use the formula for the first derivative and just throw dt in there like this, right? And the only thing we need to take care of now is the expression, sorry, this is why this expression inside of the parentheses, and we're going to be using the same formula, right? So this is going to be dy dt over dx dt, all of this over dt, and all of that over dx over dt. And now we just have to carefully assemble everything using the given information. So we have, let's find out what is dx dt. So dx dt will be simply 2t, and dy dt will be simply e to the power t. So dy dt over dx dt, that's the expression in the parentheses, will simply be e to the t over 2t. And if we want to find the derivative of this with respect to t, so if we want to find dy dt over dx dt with respect to t, we have to use the quotient rule and differentiate this. So let's do it over here. So derivative of the numerator e to the t times the denominator minus the derivative of the denominator times the numerator, all that divided by the denominator squared. So simplifying this gives us e to the t minus 1, and in the denominator we have 4t squared, but since I have an extra 2 over here, I'm going to reduce it a little, and we're going to have 2t squared. Now we put it all together. So that's my numerator. So this is my e to the t times t minus 1 over 2t squared, and we divide it all by dx dt, which we earlier found to be 2t. So the final answer for the second derivative is going to be e to the t minus 1 over 4t cubed. And now, what do we do with the second derivative? We usually use it to determine the concavity, and to determine the concavity, I'm gonna probably try to squeeze it all in here. We're gonna do the sign analysis of this function. So e to the t is always positive, so it doesn't affect the analysis of the sign. So we're only going to consider the t minus 1 term and t term in the denominator. 0 is when the function changes the sign in the denominator, and 1 is when the function could potentially change the sign in the numerator. And we can do the test points, or we can do some other analysis here, but the idea is that when t is greater than 1, the function is positive. When t is between 0 and 1, the function is negative, and when t is less than 0, it's again positive. So what does that mean? That means for negative values of t, the concavity is positive, or this way. When it's negative, the second derivative is negative, the concavity is this way. And again, when the function is positive, the second derivative is positive, we have again concavity this way. So we identified the concavity. What else can we do here? Well, we can probably identify that we have an inflection point at 1. Why? Because this is the point when concavity changed from positive to negative. And what's going on at 0? How come we don't call the inflection point there? The problem with 0 is because the concavity doesn't exist there, the second derivative doesn't exist there, and therefore the value of the function may not exist there. And if there's no function there, then there isn't anything to talk about. However, the best thing for us to do right now is probably to graph this curve and see what's really happening at 0 and 1. So let's do that. Let's enter the parametric equation. And let's analyze it. We're going to make it interesting. So t equals 0. So if we want to know which of these points is for t equals to 0, let's just throw 0 in here. So 0, we have a vertical asymptote there, vertical tangent line there, so it's not even a function. And if it's not a function, then the concave up, concave down, changing concavity doesn't necessarily result in an inflection point. You can see here the concavity did in fact change, but it's not an inflection point because this curve didn't have a function-like behavior at that point. And where's t equals 1? So we see how at this point we have the change of concavity. It went from negative to positive. Again, it's hard to spot, but again, the second derivative analysis convinces us that that's what really happened there analytically. So even though it doesn't look like that, we are 100% sure that this is an inflection point. So we discussed how to find the first and second derivatives and use them to answer certain questions and perform certain tasks for parametric curves with given parametric equations.